Have you ever wondered how the small, unseen particles around us come together to create the world we experience? Statistical mechanics is a branch of physics using statistical methods and probability theory to study large groups of microscopic entities. Think of it as the bridge between the microscopic and macroscopic worlds. It takes the erratic movements and behaviors of individual atoms and molecules and translates them into the predictable properties of matter we can observe and measure. Developed from classical thermodynamics, statistical mechanics explains macroscopic properties like temperature, pressure, and heat capacity through microscopic parameters that fluctuate around average values. Imagine trying to predict the behavior of a single gas molecule. It's chaotic and unpredictable. But by examining a large number of these molecules, statistical mechanics can predict overall behavior with remarkable accuracy. One of the critical concepts in statistical mechanics is thermodynamic equilibrium, where macroscopic properties remain constant over time. However, statistical mechanics also delves into non-equilibrium situations, which are just as fascinating. These are states where the system is changing, such as during chemical reactions or heat flows. For instance, the fluctuation-dissipation theorem helps us understand how systems respond to disturbances, and it's key to studying steady-state current flows in particle systems. Now, why is statistical mechanics so important? Its applications extend beyond physics. In biology, it helps us understand complex systems like proteins and cell membranes. In chemistry, it models reactions at the molecular level. Neuroscience uses it to study brain activity and networks. Talking about statistical thermodynamics, also known as equilibrium statistical mechanics, is to derive the classical thermodynamics of materials in terms of the properties of their constituent particles and the interactions between them. In other words, statistical thermodynamics provides a connection between the macroscopic properties of materials in thermodynamic equilibrium and the microscopic behaviors and motions occurring inside the material. Whereas statistical mechanics proper involves dynamics, here the attention is focused on statistical equilibrium or steady state. Statistical equilibrium does not mean that the particles have stopped moving, as in mechanical equilibrium, but rather that the ensemble is not evolving. A sufficient but not necessary condition for statistical equilibrium in an isolated system is that the probability distribution is a function only of conserved properties, such as total energy and total particle numbers. There are many different equilibrium ensembles that can be considered, and only some of them correspond to thermodynamics. Additional postulates are necessary to motivate why the ensemble for a given system should have one form or another. A common approach found in many textbooks is to take the equal a priori probability postulate. This postulate states that for an isolated system with an exactly known energy and exactly known composition, the system can be found with equal probability in any microstate consistent with that knowledge. This provides a motivation for the microcanonical ensemble. Several arguments support the equal a priori probability postulate. One is the ergodic hypothesis, which suggests that an ergodic system evolves over time to explore all accessible states with the same energy and composition. Another argument is the principle of indifference, which implies that in the absence of further information, equal probabilities should be assigned to each compatible situation. The maximum information entropy approach, a more elaborate version of the principle of indifference, states that the correct ensemble is the one that is compatible with the known information and has the largest Gibbs entropy. Other fundamental postulates for statistical mechanics have also been proposed. For example, recent studies show that the theory of statistical mechanics can be built without the equal a priori probability postulate. One such formalism is based on the fundamental thermodynamic relation along with a set of postulates. The probability density function is proportional to some function of the ensemble parameters and random variables. Thermodynamic state functions are described by ensemble averages of random variables, and the entropy as defined by the Gibbs entropy formula matches the entropy as defined in classical thermodynamics. Alternatively, at infinite temperature, all microstates have the same probability. 3 equilibrium ensembles with a simple form can be defined for any isolated system bounded inside a finite volume. These are the most often discussed ensembles in statistical thermodynamics. In the macroscopic limit, they all correspond to classical thermodynamics. The microcanonical ensemble describes a system with a precisely given energy and fixed composition. The canonical ensemble describes a system of fixed composition in thermal equilibrium with a heat bath of a precise temperature. The grand canonical ensemble describes a system with non-fixed composition in thermal and chemical equilibrium with a thermodynamic reservoir. For systems containing many particles, all three of the ensembles tend to give identical behavior. It is then a matter of mathematical convenience which ensemble is used. However, important cases where the thermodynamic ensembles do not give identical results include microscopic systems, large systems at a phase transition, and large systems with long-range interactions. In these cases, the correct thermodynamic ensemble must be chosen to reflect the knowledge about that system. Quantum statistical mechanics is statistical mechanics applied to quantum mechanical systems. In quantum mechanics, a statistical ensemble, a probability distribution over possible quantum states, is described by a density operator S. This operator is a non-negative, self-adjoint trace class operator of trace 1 on the Hilbert space H, which describes the quantum system. Various mathematical formalisms for quantum mechanics, such as quantum logic, provide a framework for this description. One approach to non-equilibrium statistical mechanics incorporates stochastic, random behavior into the system. While technically inaccurate, as systems do not cause loss of information except in hypothetical situations involving black holes, randomness is added to reflect that information of interest becomes converted over time into subtle correlations within the system or between the system and its environment. These correlations appear as chaotic or pseudo-random influences on the variables of interest. By replacing these correlations with true randomness, calculations become much simpler. An early form of stochastic mechanics appeared even before the term statistical mechanics was coined in studies of kinetic theory. James Clerk Maxwell demonstrated that molecular collisions would lead to seemingly chaotic motion inside a gas. Ludwig Boltzmann subsequently showed that assuming complete molecular chaos, the motions of particles in a gas would follow a simple Boltzmann transport equation, rapidly restoring a gas to an equilibrium state. This principle is encapsulated in the H-theorem. The Boltzmann transport equation and related approaches are critical tools in non-equilibrium statistical mechanics due to their simplicity. These approximations work well in systems where the interesting information is immediately scrambled into subtle correlations after just one collision, essentially limiting them to rarefied gases. The Boltzmann transport equation has proven invaluable in simulations of electron transport in lightly doped semiconductors, where electrons behave similarly to a rarefied gas. A quantum technique related in theme is the random phase approximation. In more complex systems like liquids and dense gases, it is not valid to discard correlations between particles after just one collision. The BBGKY hierarchy, Bogoliubov-Born-Green-Kirkwood-Yvonne hierarchy, provides a method for deriving Boltzmann-type equations while extending them beyond the dilute gas case to include correlations after a few collisions. The Keldysh formalism, also known as non-equilibrium green functions, NEGF, offers a quantum approach to incorporating stochastic dynamics. This method is frequently used in electronic quantum transport calculations. By understanding these advanced concepts in quantum statistical mechanics, we gain deeper insights into the behaviors of complex systems at the quantum level, bridging the gap between randomness and order in the microscopic world.